Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. In this video I thought I will show you 5 relatively small but pretty important circuits that can help you take a signal and transform it into something else. So sometimes we have to deal with signals that might come from one of our circuits or might come from external sources, and those signals are just not good enough to be able to work with them directly. So we have the need to basically transform them in a way so that they better fit our needs and satisfies some conditions that we might have. A good example would be a signal that is just too small to work with and that needs amplification. Another example would be a signal that varies in between values that are not good enough for us, and we need to basically shift that entire signal up or down depending on how we need. The cases are really varied, and I cannot tell you a single or just a handful of examples. They just arrive whenever they just simply appear, whenever we are working with various circuits, and it's a case-by-case basis. So I will show you quite a few, I will show you 5 different circuits, and I will show you the simulations on a computer and the end results, but I won't show you the actual circuits on the breadboard, simply because it would take a bit too much and it wouldn't make sense. I've tested 3 of them. I will show you the end results and I will give you all the necessary explanations. So to start with, let's define something, or maybe I should say let's just mention something. This thing that we are trying to do in English is called signal conditioning. Okay, I say in English because in my language there's no equivalent expression, and I'm pretty sure something like this does not exist in other languages as well. I'm pretty sure this is specific to the English language. Okay, so for those of you that, like me, are not native English speakers, you should know that this is actually a term that you will find in many places, or you have the chance of finding it in many places, in many documents about electronic circuits and components, and so you need to know about it. Okay, if we search on the internet on a search engine and we get to this particular definition on Wikipedia, they say that signal conditioning is basically the manipulation of an analogic signal in such a way that it satisfies the requirements of the next stage for further processing. In other words, we have a stage in our circuits that provides us a certain signal, okay, which it must be analogic in nature. It cannot be a digital signal, because the concept of signal conditioning cannot apply to digital signals. Digital signals are just 1 and 0s, okay, are just voltages that go between a maximum and a minimum, so that's a completely different kind of thing. In analogic signals, we have voltages that can vary in a wide range of values, and if these signals are not good enough for the rest of the circuits, then we must perform something that can be called signal conditioning. And this is a very generic term, okay? It's not specific. Pretty much anything you can think of doing with your signal can be called signal conditioning, okay? This is a pretty weird name to choose, but anyway, you have the so-called hair conditioner in English, which in other languages is the term conditioning, you know, implies the existence of certain conditions, but that's not true in this particular expression or in other expressions like hair conditioner. So in English they use this word differently than in other languages. Okay. So let's dive into the examples and let me explain to you what they do, and basically you will understand when to use them. Most of these examples are given mostly for how do you call it, inspiration, okay? In practice, whenever you need something like this, you will have to calculate some components around here, especially some resistors. You will have to perform your own simulations and your own actual testing on a breadboard, okay? So I will just explain to you, I will just give you these circuits as an example so that you know what they do, and so that you know when you need something to what circuit you should be looking at, okay? So first example is basically an inverting amplifier with an op-amp that has reference voltage. So the usual inverting amplifier is having the plus input, the non-inverting input, connected directly to the ground, okay? And well, as we know, it basically inverts all the values that it sees on the input. So positive voltages will be made negative on the output, and the amplitude will, the actual voltage will of course vary based on the amplification factor that we set here for this amplifier, which is set with these two resistors. I'm not gonna go into, you know, inverting and non-inverting amplifiers. You can find plenty of videos on YouTube. Just search op-amp inverting or op-amp non-inverting, and you will be able to learn about these two very basic configurations, okay? Now, unlike a simple inverting amplifier that has the plus input connected to the ground, we have it connected to a certain reference voltage. And if this happens, then we have, let me simulate so I can show you better. Then we have essentially an inverting of phase, but we also have a shifting of all the values on the vertical, okay? So we are having a sort of offset voltage applied to the output signal. So, in other words, we can use this circuit whenever we are having something like this, like a signal. Take a look at the blue line. In my particular example, I've chosen a signal that goes from 0 to 1 volt, okay? And that has a linear response, a linear change in time. And let's say that we want to have the exact opposite of this, which is the red curve, but we still want our signal to vary from 1 to 0, okay? We don't want it to go down in the negative range, because if we would connect this plus input to the ground directly, okay, we would have an inverse signal that goes into the negative values. So whenever the input signal grows from 0 to some positive value, the output signal will diminish from 0 to some negative value. Okay, but let's say that we don't want this. We actually want the inversal of this input signal, but we want to keep the minimum and the maximum value between which this signal varies the same as the input signal. Okay, so we have 0 to 1 volts. Well, we want the output voltage to go also from 0 to 1. Okay, so in that case we need to apply a reference voltage to this plus input. Instead of connecting it to the ground, in other words placing it at 0 volts, we need to give it a reference voltage, and based on this reference voltage the signal will go up a bit or more. Okay, and the output voltage will be, mathematically speaking, 2 times the reference voltage minus the input voltage. Okay, so in other words, if we have our signal that goes from 0 to 1 volts on the input, and we want our output to go in reverse from 1 to 0 volts, then the difference between 0 and 1, the average, sorry, the middle point between 0 and 1 is half a volt. So we need to set half a volt for this reference voltage, and that's when we will get this result on the output. The input signal exactly flipped around, and it never going below 0 volts. Okay, it oscillating, varying, not oscillating, but varying between the same minimum and maximum as the input voltage, but in reverse. Okay, now this of course works when we have these two resistors of equal value. It doesn't really matter what value. I've put 10k just for, you know, the sake of having something, but the value itself doesn't matter. What matters is that this formula, this mathematical formula, works for these two resistors of equal value, so that the entire amplifier has an amplification factor of 1 or minus 1, if you want to see it this way. If you would have a different amplification factor, then you would have different results here, and the formula would not be this one. It would not be valid anymore. Okay. Before I go to the next examples, I should have mentioned, and I forgot, that pretty much all of these examples, with the exception of the last one, are examples with op-amps that are being powered from differential 12 volts. So we have relative to ground, we have both positive and negative 12 volts. Okay, this is just to be clear how this works. Okay, so let's say that we are not in this case, when we just want a reversal of a signal. Let's say that we are in this particular case. We have an input signal that is very small in amplitude. In my example, it varies from 0.2 to 0.3 volts, so only 100 millivolts amplitude. And it also does not vary between 0 and 100 millivolts, but between another voltage. And we don't like that. We would want two things basically on this input signal. Again, take a look at the blue line. We would like to amplify the signal because 100 millivolts is just too little. And in my case, I chose to want a 1 volt signal on the output. So basically, I need an amplification of 10 from 100 millivolt to 1 volt. And the second thing that we want is to basically have the signal vary from 0 to some voltage, in my case from 0 to 1 volts. So we also need to apply some sort of offset to drag this entire signal down. If we would simply create a non-inverting amplifier, okay, we would have the signal amplified with all of its values. So a signal that goes from 0.2 to 0.3 volts amplified 10 times, it will give a signal that varies between 2 volts and 3 volts. And yeah, maybe that's okay for us, but maybe that's not okay. Okay, maybe we want the signal to get down to 0 volts and start from 0 to 1 volt in this case. Then this ground resistor needs to be connected to some reference voltage, and this reference voltage needs to be in accordance to this formula. So for this particular amplifier, for this particular circuit, the output voltage will be the input voltage multiplied by the amplification factor. Okay, the amplification factor is given by the ratio of these two resistors, and like I said, if you take a look at videos regarding inverting and non-inverting amplifier with op-amps, you will know that the amplification factor is 1 plus R5 over R6 in this case, R5 divided by R6 in our example. Okay, so this is the amplification factor, which I've denoted A indice V here. So we have the output voltage equal as a mathematical formula with the input voltage multiplied by the amplification factor minus 0.9 multiplied by the reference voltage multiplied by the amplification factor. Okay, this is the mathematical formula for this particular amplification circuit. So in this particular case, if we want the output voltage to drop down to 0, we would need to have a reference voltage of roughly 0.222 something volts. Okay, then on the output with red, we see that we would have exactly the input signal but amplified, goes from 0 to 1 volts, and also dragged down to start from 0 volts. Okay, good. Now these were two examples that were relatively simple and for which I could give some mathematical formulas. For the rest, I cannot. They will be more complex, and you cannot have a simple formula because the output signal depends on many factors. So from now on, we just need to understand the basic principle of these circuits, how they work, why they work like that, and basically when to use them. Now, in these first two examples, we had linear input and linear output. However, what if for a certain linear input, when I say linear input, I mean a signal on the input that varies linearly with time or whatever, that it simply varies linearly. Let's say that we want to have a sort of a logarithmic response on the output. Okay, so we basically want to calculate something like a logarithm, as close as possible of a logarithm, but also with some amplification factor. Let's say that we want the output signal to start from the same value that the input signal starts, to stop at roughly the same value as the input signal stops, but instead of being a straight line, we want it to have this specific curve, specific logarithmic curve. Okay, Then we have some options that we need to look at. And we have this potential circuit that can do the job. Now, before I start explaining this particular circuit, let me just explain how exactly can we turn one line, a signal that basically has a linear variation, into something that has a logarithmic or exponential variation. Okay, we can accomplish this by having an amplifier with an amplification factor that changes based on the input voltage, so that the higher the input voltage is, the lower the amplification factor will get, and the lower the input voltage gets, the higher the amplification factor we will have. Okay. Now, an op-amp's amplification factor is given by two resistors, and as we see here at the center of the circuit lies an op-amp configured as a non-inverting op-amp. Okay, so we have R8 and R11 as feedback resistors in the classical non-inverting configuration. So in order for us to change the amplification factor, we need to change the values of these two resistors, or at least one of them. So a first option would be to change the value of R8 in our example based on the input voltage. However, that's quite difficult because R8 is not connected to the ground, is not connected to the positive power rail. It's connected to 2 points in between, and that makes it more difficult to change its value, and not necessarily the value of that resistor itself, but to change the resistance between those 2 points. It's more difficult. Okay, a simpler solution would be to change the value of R11 in our case, because R11 is connected directly to the ground. We could theoretically pass it through a transistor and have it open and close, but I've found out that that poses some problems as well, and in the end I just abandoned that idea and I went for the third option that we have, which is to basically feed the op-amp, the non-inverting input of the op-amp, with a fraction of the input signal based on the input signal, essentially. Okay, or based on the output signal. Well, it doesn't matter all that much. So this is what I've done here, essentially. We have the input signal going through a 100 kilo ohm resistor into the non-inverting input, but this non-inverting input is also connected to the collector of an NPN transistor, which has the emitter connected to the ground. Essentially, this resistor and this transistor form a voltage divider. Okay, it's not the usual voltage divider created with two resistors, but only with one resistor and one transistor, because let's remember a transistor, especially a bipolar transistor, essentially works as a variable resistor. Okay, so by varying the equivalent resistance between its collector and emitter, it can drop the input voltage on the input of the op-amp from the maximum value, which is given by the input signal, down to zero. It can actually get down to zero if it needs to. Okay, so we need to make this transistor turn on and off, and not just on and off, but start to turn on gradually based on what voltage we have on the output. And for that, I'm taking the output voltage and passing it through a couple of resistors into a diode, a rectifying diode. Okay. I have come to these values by some of these values were chosen arbitrarily initially, and then they have been adjusted by repeated simulations. Okay, I don't have a particular formula. I have chosen to have roughly an amplification factor of something between 3 and 4 for this op amp, so this is why you see R8 and R11 with these values. And the output signal gets passed through 1.3 kilo ohm resistor. In my case, I found it to be good enough. And passed into this rectifying diode. The idea is that if we take a look at the data sheet of a rectifying diode, I've chosen 1N4148, which is the very well-known rectifying diode, pretty cheap and widely available. At some point in the data sheet, we will see a graph like this with forward current and forward voltage, and the creators, the manufacturers, will basically tell us what forward voltage should we expect across the diode for that particular forward current. Now, if we take a look, if we pay attention to this graph, we will see that the forward voltage axis is linear. However, the forward current axis is logarithmic. So basically, what does this tells us? Well, this tells us that if we inject a current through the diode and we vary this current exponentially, then we will get a linear increase in forward voltage. Or the opposite is true as well. If we inject a linear current, a current that varies linearly into the diode will provide us with a logarithmic voltage across it. So essentially, in order to convert a linear signal into a logarithmic signal, I have used this particular characteristic of rectifying diode for it to help me make this this transition, this transfer, okay, this exchange. Now the voltage of the diode herself most often is not enough to properly control a bipolar transistor. So I've chosen to have a bit of extra voltage, and in order to do that, I have placed a smaller resistor in series with the diode, so that it has an extra voltage drop, so that overall the voltage drop on both of these components is higher, slightly higher than the voltage for a transistor to open, and therefore we can play a bit with how fast or how slow we are turning on this transistor. And this is given by the other voltage divider here, made by these two resistors placed in parallel with the diode and its associated resistor. And basically these are set to have a certain value so as to turn on this transistor faster or slower. The smaller the value this resistor has, R17 in our case, the faster the transistor will turn on, and the more bent the curve on the output will be. For example, if I make this 10 times smaller, I make it 100 ohms, we can see that the output voltage bends a lot faster. If I put 2 kilo ohms, we will see that the output voltage has a much smaller curve. Okay, for this simulation, for this particular transistor, and this lower resistor of 6.8 kilo ohms, I determined that 1 kilo ohm seems to be the right value in order for the output voltage to vary between the same 0 and 2 volts as the input voltage, but with the exception that we will get this sort of logarithmic curve. Okay. R19, by the way, it's calculated by basically thinking of taking into account the maximum output voltage, subtracting the voltage that we want the diode to have across it, and then dividing that resulting voltage to whatever current needs to be inserted into the diode so that we will have that particular voltage across it. And this has to be taken from the data sheet of that particular diode. Okay. We also have an extra component here that in practice might not be necessary. We have this capacitor across the diode and this smaller resistor. This is because depending on the frequency of the input signal and the amplitude and other factors, this circuit has the tendency to oscillate. Okay, for example, if I disable this capacitor, we see that it tends to have some oscillations. The whole circuit tends to have some oscillations at smaller values. Okay, so I needed to place it in order for this circuit to work properly. In practice, you need to see for yourself if in your case you need it needs to be smaller or bigger, or it can be completely removed. Okay. Because in my case, I've tested this circuit on a breadboard with 40 Hertz signal instead of 1 kilohertz like in the simulation, and I needed to remove this capacitor completely because with this capacitor the circuit was starting to oscillate. Without the capacitor, at 40 Hertz it was working perfectly. So in my case I needed to remove it. Also for my transistor I needed to set this to 1.5 kilo ohm because 1 kilo ohm was just too small value. So again, you know, your millage may vary, as you guys say. So if we are to take this response curve and to compare it with an actual logarithmic curve calculated mathematically, we would get this. I have overlapped 3 different graphics in this image with the dark bluish color. This external curve is the actual mathematically calculated logarithmic curve. The smaller red curve that is barely visible, it's very close to this theoretical curve. The smaller red curve is the one that we have here with our simulation, and this rather nasty thick purple curve is the one that we have in practice, the one that I've actually obtained on the breadboard, testing this practically. Okay, so we see that the 3 curves are pretty close to each other. So even though in reality we are not obtaining a true logarithmic curve, we are obtaining one that is pretty close to a logarithmic curve. Okay. And by the way, this is the signal for this example. With blue we have the input signal, which is triangle, and with yellow we have the output signal, which is the sort of logarithmic one. So this is an okay circuit to use when you want to convert linear to logarithmic. Now, the problem with it is that the curve is not so... the curve can be manipulated a little bit, but the biggest problem is this potential for oscillations. And this is due to the fact that we have a transistor that limits the input voltage here based on the output voltage here. Now, theoretically, we could do this so that the input signal is generating this voltage. However, I have chosen to test a separate signal, a separate circuit, sorry, and take a more direct approach to this particular problem. And this is what we have here. We have a more complex circuit that has two operational amplifiers. Well, it has two operational amplifiers because I wanted to invert the signal at the end. But anyway, we have a completely different principle of working here. Okay. We have the input signal that is fed directly through a resistor to a rectifying diode, so that the input signal directly generates voltage across this diode. Okay, this resistor, of course, must be calculated based on the maximum voltage on the input, the voltage that we desire on the diode, and the current that the diode needs to have in order to provide us that particular voltage. Just like in the previous example. Now, after what we have done this, and we basically have a voltage across the diode that varies sort of logarithmically, we take this voltage, which is very small. It varies between 0 and some 0.7-ish, give or take, and we need to amplify it. Okay, and for that we are placing it in a non-inverting amplifier. R21 and R22 form the classical non-amplifier feedback configuration of resistors. And if I would disable this diode, I will tell you in a moment what it does. If I would disable this diode and we would be taking a look at the output of this amplifier, which is the purple curve here, okay, we would see that it varies kind of exactly like the input voltage between 0 and 2 volts, and it has this particular curve. Okay. Now, this particular curve is actually a bit farther away from the logarithmic curve. This is much closer to the logarithmic curve. So if I am to go back and forth there, just so you can compare this red curve here with this purple curve here, you can see that this fourth circuit that I'm showing you right now gives a response that is farther away from a logarithmic response. Okay, but let's say that we don't care all that much about having a pure logarithmic response. We just care about having a sort of a curve, the output signal taking a bit of a curve. Okay, and let's say that this curve is not enough. If it's enough, then this is all that we need to do. If this is not enough and we want a more pronounced curve, then we must make it so that the amplifier changes its amplification factor based on the output voltage, in the sense of reducing the amplification factor if the output voltage goes above a certain level. And this is why we have this extra branch here in the feedback network of this op-amp with this rectifying diode placed like this and this extra resistor. Basically, when this rectifying diode receives enough voltage across it, it will start to open and it will pass current, which will essentially place this resistor, Ru26 in our example, more or less in parallel with Ru21. And if this resistor is considerably smaller than this other one, then we will have this more flattening curve happening here. And we see that this is what happened with our purple curve, okay? It flattened a bit more, and instead of going up to 2 volts, it goes up to only 1 point something volts, okay? And of course, this resistor, this resistor's value matters a lot. If we make a higher resistor, then this curve will be smaller. If we make a lower resistor, then this curve will be sharper, will be much more sudden, okay? And now, if we're okay with this curve, fine, perfect. But if we're not okay and we want to invert it, like in my case, then we can take it and insert it in a circuit that looks pretty much like the initial, the first circuit that I've shown you earlier. Except in this particular case, we do have an amplification factor. It's not much, it's just 2.2, but it's still an amplification factor. And instead of placing just a theoretical voltage reference, I have placed an actual voltage reference made with a resistor and 2 diodes, so that I can simulate this better and make sure that I can do this better in real life, okay? So I've placed these 2 diodes, a rectifying diode and a Schottky diode, in series with a resistor. Again, these are used so that a certain current passes through them, and therefore they develop a certain voltage across them that can be taken as a reference. And this voltage, I am placing it into the plus input of this second op-amp. And this is how, in the end, after 2 op-amps and this entire circuit, we have the red curve here in our graph that looks like this. That looks like the opposite of the purple curve, and also much bigger because we have an amplification factor, okay? Something like this I needed for a circuit that I worked on and that I will show you in the next video. So whenever we need something like this, we can think about this particular circuit, okay, and adjust it to satisfy our needs. Now, if we want something like this, but we don't care that much about all of this curvature, if we can work with a flatter curve that has basically 2 straight lines, then we can employ a fifth example, a fifth circuit that is much simpler. It has only 1 op-amp, fewer components around, just 2 diodes, and also this fifth circuit is different from all the other 4 in the sense that I've simulated it with a single power supply of 4 volts and a rail-to-rail op-amp, because in my case this is what I needed to have in the end. I need to, for this circuit to work, powered by 3 AA batteries, 1.5 volt batteries, that in total they give 4.5 volts, but when they're consumed they can drop down to 4 volts or sometimes even less. So this is why I simulated this circuit like this. But of course you can adapt it to other voltages and other powering schemes. Anyway, This voltage works, the circuit works kind of similar with the previous ones, except, you know, if I go back and forth between the previous one and this one, you're going to see that, taking a look at this red curve, for this last circuit, the curve is much straighter. It has just a little bit of a round shape at some point, and before that and after that, we basically have a straight line. This is the major difference between this circuit and the previous one. The previous one was more complex, but it gave us a more rounded curve. This one gives us a flatter curve. Okay, again, I mentioned this because sometimes this curve is good enough for what we need. For me, it was. So it's good to know that this particular circuit can be used to obtain these particular results. The idea of the circuit is simple. This is an inverting op-amp. Okay, the input signal goes into an op-amp that inverts it. Essentially, R28 and R27 form the feedback resistors that set a certain amplification factor, and that are placed such that the op-amp is in inverting mode. However, we have two extra things. First of all, we have an offset voltage on the positive input, on the non-inverting input, and this offset voltage is again created by injecting a relatively small current into a rectifying diode, and that diode will provide a certain voltage, around 490 millivolts in my case, when that small current is being was introduced. In my case, the current was about 100 microamperes, and this reference voltage is used by the op-amp to essentially flip the input signal around, but not around 0 volts, around some other voltage. Essentially, this is identical to, more or less identical to the first example that I've shown you. There's one more trick involved here, and that is with this relatively small resistor and this diode, which is a Schottky diode in this particular case, flipped around in polarity. So if here we had a rectifying diode with the cathode towards the inverting input of the op-amp, here we have a Schottky diode with the cathode towards the output. In other words, this circuit has a relatively high amplification factor given by R27 alone and R28, from the input signal going from 0 to a certain value, which happens to be around half a volt in this particular example. And from that point on, until then, the Schottky diode is turned off. It doesn't have enough voltage across it to basically start to open. And until that, starting from that point, when the diode starts to conduct, it will place this lower, much lower value resistor in series with this one. This lower value resistor will dominate essentially, and so the overall amplification factor will diminish a lot. Okay, it will go from 5.6k divided by 1.3, from an initial 4.3 amplification factor, it will go down to approximately 0.25, okay, 0.2, 0.3. So this is how we obtain basically two curves, two different curves that have a different slope. We have a very fast descending curve initially, if we can call it like that, and then after the diode starts to conduct, we have a much slower descending curve. Okay, again, this is a simplified version of this example, and if it's good enough for us, then it's worth taking this into account. Okay, and I forgot to show you, so this previous example, okay, this previous example, which attempts to have a more logarithmic response and an inversion, in reality, you know, it works like this, which is not very far from what we simulated here. Take a look at the red curve. In my screenshot is the yellow curve. It's different because the intersection point here is essentially half a volt, whereas in my simulation the intersection between the input and the output is, well, actually it's not far from half a volt, is 0.46 volts. So yeah, so this is the practical example, and this fifth example that I have shown you at last, that have a much straighter response curve, in reality also checks out, and intersection is precisely at half a volt. Okay, the colors are inverted, so now we have yellow the input signal and blue the output signal, but essentially they are they show the same thing. Okay, so yeah, so sometimes we need to employ one of these examples. Okay, one of these 5 circuits need to be used in order to manipulate our signal, in order to obtain something. Okay, I will give you the next example where I will show you a much larger device that includes such circuits. I will show it to you to basically exemplify where I had the need to do this, to convert a linear voltage into a reverse logarithmic voltage, and you know, why did I chose what I chose. So I hope this was useful to you. I hope you've learned something new, and now if you need something like this, you know where to look at. I will place this simulation and all of these screenshots. I will make an archive with them, and I'll place the archive on Patreon. So if you want to, you can download them from there. If not, you know, you're free to redraw the schematics from the screen. Thanks a lot for watching. I hope you found it useful. If you did, please hit the like and subscribe button if you want to see more videos from me teaching you electronics. Also, if you enjoy my work, please consider subscribing on Patreon, helping me financially on Patreon. The faster I can buy components and maybe even lab devices, the faster I can learn all sorts of things, and I can come here and teach you as well, so that you don't have to spend so much time and energy learning all of these things as I am spending this time and energy. Thank you very much for watching. I will see you in the next video. Bye bye.